Welcome to another astronomy lecture. This lecture is going to be pieces of chapter 8, 9, and 10 from the text here. So mostly this is about Earth and then sort of Earth-like planets. This is one of the first pictures taken of Earth, the whole globe. Pictures known as the blue marble. I guess we kind of take it for granted that this is what the Earth looks like, but seeing it in sort of the black backdrop of space and this emptiness, it gives you, maybe makes you think a little bit about our place in the universe. One of the things that makes Earth stand out among the other planets is its active geology. There's some activity, volcanic or tectonic activity on some of the other planets that we're going to look at, but pretty much nothing on the scale of what goes on Earth. We have active volcanoes, we have tectonic plates that are constantly sort of moving around the surface of the Earth and sort of reforming the surface of the Earth. The Earth's interior is still quite hot. Right? So when I was telling you about the formation of the planets, we're talking about planetesimals smacking into each other and heating up and melting the protoplanets. And then we get that differentiation happening where all the metals sort of accrue in the center, and then you get more of the rock on the outside, and sort of gas on the outside of that. So as it turns out, Earth's interior is still quite hot, and it will be quite hot for a good long time. And part of that is just the leftover heat from the formation. Billions of years later, it's still hot inside there. There's also a substantial portion of heat that comes from radioactivity inside of the Earth. So that's elements that decay radioactively, so the nuclei sort of break apart or fall apart in some way, and in that process you end up releasing energy that heats the surrounding environment, and so that radioactive decay is also adding to the heat of the Earth and keeping it going for quite so long. Just looking at some of the numbers, and again, sort of standard to measure the distance, at least planetary scale distances in astronomical units. So that's just the distance of the semi-major axis of the Earth, halfway across its elliptical orbit. And the period we usually measure in Earth years. The mass, diameter, the radius. We talked about escape velocity a little bit in the first lecture or two. Density, about 5.5 grams per cubic centimeter. And atmospheric pressure also is another standard where one bar, is the standard pressure at sea level on Earth. And so when we talk about some of the other planets, we'll talk about it in relation to Earth, because that's the one we're on, that's the one we know best. Right? How far away from the sun they are, how long they take to revolve around, and what the pressure is, the atmospheric pressure is, if they have atmospheres. Should note maybe that I told you that astronomy generally is studying the things that are not on Earth. So it might seem a little bit odd that we're going to talk about Earth, but despite the fact that for a long time, at least in sort of the Western world and Western thought, Earth was like the center of the universe, and it was sort of different from the other things, the other planets that we saw, stars and all that good stuff. Turns out the Earth is a planet not unlike many other planets that we see. So the fact that we're actually on Earth and we can study Earth very intimately is very helpful for understanding planets and geology and planetary activities like tectonic plates, volcanism. So kind of using the fact that we're on Earth and it is a planet to understand at least something about planets. And particularly sort of more rocky planets like the inner planets of the solar system, the terrestrial planets. You've probably seen this picture before, the makeup of the Earth inside of the Earth, right? So the crust is this relatively very thin layer around the outside of the planet. Below that is quite a large region that we call the mantle, and within that is then the core. So something we've realized is that the core and the inner core are very hot. That's where a lot of the heat is left over from the Earth's formation, and that heat needs to, or wants to dissipate, it wants to move out. And so it ends up heating up the mantle, and you get sort of this convection or this like heat that flows from that really hot core out through the mantle and up into the crust, right? And that's basically or that process of convection, of like this heat moving up and liquefying areas and those areas rising up to the surface, is what causes our volcanism, what leads to the tectonic plate activity and the shifting around of the Earth's crust. Now, how do we know about the inside of the Earth, right? Because it's very hard to study any portions of the Earth besides its crust. Right? The crust, you need to go down at the very least like 4 or 5 miles below the surface to get to the mantle. Right? So it's quite difficult, and that's even if you're starting like on the ocean floor, then it's only that deep. Right? On the continents, it's dozens of miles that you need to go down. Continental crust is a bit thicker. We'll look at that more in a minute. But we're able to study the interior of the Earth. One way we do that is through something called seismic tomography, where you use the vibrations or the waves that are created from things like earthquakes or very large explosions. And we have these like survey spots around the Earth, these geological sort of survey spots that can pick up those waves. From those patterns that we see, we can determine sort of how those waves move through the interior of the Earth. And just to let you know, when waves like move through material and like the properties of that material change, say like you're going through some liquid and all of a sudden it gets more dense, right? Then the speed of the wave then changes. You don't need to get too deep into that, but essentially as waves are moving through different kinds of material, they're going to sort of adjust their properties as they go through. And by sort of looking at the overall effect of that, right, having these sort of survey spots where we're picking up all of these vibrations in the end, we can kind of trace back and look and make a map of the sort of stuff that these waves went through. So this is a process that's somewhat similar to something like echolocation or ultrasounds. So in the animation on the left, right, there's like, I think it's the actual data maybe, or representation of data from observations that were made at some of these survey sites. They're dotted along the globe there. There's a couple of different places shown on there. But there was an earthquake, I think somewhere up in Alaska or in that area, and the animation gives you an idea of what kinds of things happen to the waves that are generated, or those vibrations that are made by the earthquake way up here, reverberate all throughout the interior of the Earth. Along the top, you actually see the results or the data that gets taken up by some of these survey spots. And it's complicated, but we're able to put that information together in order to give us an actual idea of the different properties of the interior of the Earth. From that, it seems that, yeah, the mantle is this big area underneath the crust, and then inside of that there's a different region, the sort of outer core, and then even within that there's this another sort of different region. At the very least, just take that away, I guess. However, it's certainly not as clean cut as some of those pictures might have seemed or might have made you think. Right? Like in the first picture of the Earth's core, it's just like these spheres or like shells around spheres, right? Very clean cut, like there's this specific sort of edge to the core, specific start to the crust. Yeah, nothing's that clean cut in nature. So to give you an idea of the sort of messiness or the complicatedness, I have a couple of animations here. One is showing convection regions in the mantle. And so that's where heat is sort of welling up and changing the properties, like heating up the stuff that it goes through. That heat comes through and it will maybe liquefy areas that it goes through, or in some ways adjust its properties. And so I think on the right side, it's showing the heat, the warm upwelling. So that's heat coming from the inner core, or from the core, and moving in these sort of plumes out towards the crust through the mantle. So heat actually comes up, but then stuff that's in the mantle that's sort of more closer to the crust is cooled off, right? And the cooler stuff wants to then settle back down towards the core. And on the left there, you have regions of like this down wellings, right? These cooler parts of the mantle that want to kind of move back towards the core, and then they'll start to get heated up again. They'll flow back out in these sort of plumes. One other interesting example of this sort of complicated nature of the interior of the Earth is something called large low shear velocity provinces. Complicated sort of name, but it's indicating that essentially they're very big, and the velocity of waves that travels through them changes quite significantly, so that tells us that there's something different going on. also I think known as superplumes. And I don't recall off the top of my head when they were sort of first noticed, but they're still quite mysterious as far as science is concerned. Don't really know exactly what's going on with them, but they're these sort of very, very large blobs, they just kind of call them blobs too, outside of the core. So yeah, the interior of the Earth is sort of differentiated into these regions, like the inner core, sort of the outer core, the mantle, and the crust, but it's not this like really clean-cut, smooth thing. Right? It's complicated. It's messy. Thinking a little bit more about the Earth's crust then for a second, it is made up of sort of two main kinds of rock. One is the oceanic crust, because it's mostly what makes up the ocean floor, and it's something like 6 kilometers thick on average. That's maybe 4 or 5 miles, and it's made up of volcanic rock called basalt, which primarily is silicon, oxygen, aluminum, and magnesium. And then the other kind is what we call the continental crust. It makes up most of the continents, and it's much thicker than the oceanic crust, something like 20 to 70 kilometers thick. Covers a little less than half the globe. The oceanic crust covers a little bit more than half. And it's made up of volcanic rock as well, but a different kind called granite. So like I said, the crust is the easiest part for us to access, but it only makes up 0.3% of the total mass of the Earth. So this is going to be sort of a recurring theme as we look at some of the other terrestrial planets, is that they're mainly made up of two sort of areas on the surface, which is this sort of continental-like crust that's thicker and higher, and this oceanic crust that's sort of lower and thinner. One other thing about the Earth I wanted to point out before we move on is that it has a magnetic field. You probably know, right? That's the reason that compasses work, they point towards the North Pole, that sort of thing. It's very nice that we have this magnetic field because it tends to protect most of the Earth from stuff that comes at the Earth that could be harmful to us, particularly stuff coming from the sun. If you remember, I mentioned the solar wind when we were talking about the formation of the solar system, and that solar wind is just an ongoing thing. The sun's always kind of blowing out stuff, and sometimes more than others. So we'll probably talk about some of the more violent events that the sun goes through, like coronal mass ejections. But even besides those sort of noticeable ejections, there's kind of just this continuous wind of stuff coming. And a lot of it is electrically charged. And if you didn't know, then electrically charged particles are going to interact and feel a force from magnetic fields. And so a lot of that stuff coming from the sun ends up feeling this force when it encounters our magnetic field, which basically pushes those particles towards the poles of the Earth, right? So they end up wanting to follow along the magnetic field lines, and they'll come around and then get sort of swooped in under the North and the South Poles. So the reason that we even have the auroras, the aurora borealis, the aurora australis, is that these charged particles, these stuff coming into the Earth and getting directed towards the poles by our magnetic field. And that stuff then crashes into the atmosphere and excites some of the gas in the upper atmosphere, and then it de-excites and lets off some visible light. Yeah, so there's some terminology here. We don't need to worry too much about it, right? Just that the Earth has this magnetic field that protects us from a decent amount of stuff that might otherwise harm life on the planet. And then also, as I pointed out, for the interior of the Earth, or like the picture that we usually see of the interior of the Earth, it's not as nice or static as like some of these pictures might seem. So I have this animation here that gives you a little bit more of an idea of the sort of active nature of the magnetic field, right? It's sort of constantly changing a little bit how it's actually set up. And when you look at some picture of a field, like a magnetic field, a lot of times they're drawn with these lines, and you don't really need to know this, but just to mention that the lines are an indication of the field, and how close together those lines are is sort of an indication of how strong the field is. In the image here, when it changes, right, sometimes those lines get closer together, and that's indicating the magnetic field is increasing in places, or they're getting pushed apart and it's getting weaker. I think this animation is actually of a ejection of material from the sun that comes and hits the Earth's magnetic field, and it actually temporarily sort of weakens it a little bit. It kind of strips away some of it temporarily. And finally, just to point out that magnetic fields are produced by the movement of electrically charged objects. So like electrons, right? One of the constituents of the atom is an electrically charged thing. And protons, also electrically charged things. Atoms themselves are generally neutral because you have electrons and protons, and so pluses and minuses, they kind of cancel each other out and you get a neutral object. But the thought is that in the interior of the Earth, and the inner core in particular, is so hot still in there that the atoms that make up the interior actually have some of their electrons kind of pulled off. Like it's so much heat, there's so much energy that's added to all those atoms that some of the electrons are just sort of kicked away from the atoms. So what you're left with is overall there's charged material, right? Electrically charged material, and the fact that the whole Earth is rotating and the interior, the core is also rotating, means we have electrically charged objects that are moving. That creates magnetic fields. As it turns out, if you have electrically charged objects kind of going in a circle, then they tend to create a magnetic field that basically looks like a bar magnet. And so that's why we get these field lines that sort of come out of the top and go at the bottom. This picture like this. But they're also adjusted a little bit because the sun is pushing those magnetic fields away, or sort of molding them away. And so you get this one side that actually goes out a decent ways towards the sun, but then the other side gets pushed away and it goes quite far in the opposite direction. Last thing to note here is that in that animation you might notice that there are other lines to the left that don't really seem to be part of the Earth's magnetic field, and this is because the solar system just has magnetic fields that permeate the space, like the solar system, right? And most of those magnetic fields are from the sun. The sun also has a lot of electrically charged things that are moving around, so it creates magnetic fields. And then even throughout the galaxy, there's magnetic fields all over the place, and those are generated by like stars, like our stars, or other electrically charged things that are just kind of moving around. Okay, enough about the Earth. Let's talk a little bit about the moon. Just some nice images of the moon. The left side in the top there is the side facing Earth. The right side is the side facing away from Earth. And something you might notice is that the side facing Earth has a lot more of those dark areas, kind of more smooth areas, versus the side facing away has a lot more of those circular areas, right? All those little circles then are impact craters from asteroids and comets that have impacted the moon. And the moon, the orbit of the moon around the Earth is sort of special in a way in that there's always the same side of the moon facing the Earth. It's, I forget what the term exactly is, like tidally locked or something like that. Like somehow in its orbit it end up sort of turning around and rotating around the Earth and rotating on its axis in such a way that there's one side of the moon always facing us. And that side that's facing us, there's not a lot of, or there's much less incoming objects that are going to hit it, right? Because the Earth sort of acts like a little bit of a shield. So the side facing away has a lot more of these impacts. The image here is of an astronaut, I think it was actually a geologist that was sent up in Apollo 17, and they took a bunch of samples. Actually, throughout all the manned missions to the moon, they took samples and brought them back. So a lot of stuff we know about the moon is from samples that were collected during the Apollo missions. So something that's particularly interesting about the moon, and trying to understand how it came about, is when you look at some relationships between the elements and the isotopes of elements on the moon and compare them to the Earth. So particularly isotopes of oxygen. So if you remember, an isotope is an element that has a varying amount of neutrons. Oxygen is 8 in the periodic table, meaning it is defined as having 8 protons in its nucleus. Sort of the most common type of oxygen is the one that also has 8 neutrons. So it has 8 protons and 8 neutrons. So altogether, there are 16 things in the nucleus. Right? So that's why the most common one we call oxygen 16. However, there are other isotopes, right? You can have one more neutron, right? Then there's 17 things. You call that oxygen 17. You have 2 more neutrons, so there's 18. That's what you call oxygen 18. So as it turns out, when we look at the sort of relative amounts of oxygen 16, or the most common, to oxygen 17, that isotope, and compare that with sort of the amount of oxygen 16 and oxygen 18 on the Earth and the Moon, and we're looking at the ratio of these isotopes, compare them together, the Earth and the Moon have remarkably similar ratios of these isotopes. This graph in the bottom here, we might not need to understand all that much about it, but we can say at least that if you look at the line, that solid line drawn here, that's Earth. Right? Those are the relative ratios of isotopes for oxygen on Earth. And there's some other ones on there. There's Mars, and there's also Vesta, which I believe is an asteroid. Those don't really fall along the same kinds of ratios, right? They don't fall on that line that is Earth. But if you look at the Moon, remarkably similar to Earth, right? Pretty much on that line. So there's some kind of clue of the origin of the Moon. However, there are also substantial ways that the Moon is quite different from the Earth. One, just looking at its overall density, right? The Earth is about 5.5 grams per cubic centimeter. The Moon is only like 3.3 grams per cubic centimeter. So it actually has a much larger rock, like silicate rock content, and much lower metal content. And in fact, we have found H2O on the Moon, and very, very cold on the Moon, and it's all in this sort of like frozen and like intermixed form, I think, in the soil of the Moon. However, if you were able to pull all the H2O together and have it in liquid form, it's estimated there's enough H2O on the Moon to fill up a lake that's like 100 miles across. There's quite a lot of H2O there. But getting back to those similarities and differences, this is sort of the current thinking of how the Moon came about, right? How we got our Moon. And it's basically that there was an impact sort of early on in the Earth's formation, right? Remember I was saying that the formation of the solar system, it's thought that there were a number of other protoplanets that were still floating around, orbiting around in the solar system, besides the ones that end up becoming the planets that we know of. It's thought that one of those protoplanets, that was about the size of Mars, impacted the Earth. And in doing so, it pulls away a decent bit of Earth's mass, right? The crust and sort of the mantle. And that material, is still gravitationally attracted to the Earth, and so it kind of gets pulled around and starts to orbit this sort of ring. And then that ring eventually sort of coalesces and pulls together to each other gravitationally and will come together enough that we eventually form the Moon. There have been a number of different theories to explain the origin of the Moon over the years. This one is sort of the current one that seems pretty reasonable and is able to be reproduced through computer simulations to actually give us a Moon very similar to what we have. And yeah, but the fact that it comes in and impacts, it takes away a lot of stuff from the Earth's crust and mantle, which is mostly silicate rocks, but doesn't really take away much from the core, right? So that's why, or one way of understanding why the Moon ends up having a much larger rock content than metal. But by actually being like made up of parts of the Earth, it also explains a bit why those isotope ratios are so similar. And that animation there is kind of just a cool way of seeing this impact happening. It doesn't go quite as far as all that stuff then accruing again and forming its own sort of mass into the Moon that it is now. And an interesting fact, that object that impacted the Earth is nowadays called Theia. That's the idea anyway. Alright, well, I'm going to talk a bit about some of the other terrestrial planets. And going fairly quickly, I'm just going to give you some sort of information, like bullet points about these different planets. And and I think next time we'll move on and talk about the Jovian planets, the gas giants, sort of work our way out of the solar system. Right, so the first one we'll talk about is Mercury, closest to the Sun. The image on the left is an actual photograph. The actual color of Mercury is a little bit weird. It's basically grayscale, but you might see images of Mercury that actually seem to have some color. If you look at it, if you're able to see it with your eye, it would probably be almost gray. You might have a little bit of twinges of color, but it kind of looks like the Moon overall. The middle image is a very simplified diagram of the interior of Mercury, and it has this huge core. Right? And the core, like the Earth, is mostly made up of metal. And so it turns out that Mercury has a very high metal content. And then this picture on the left here is sort of like an elevation picture, where the color, like the dark blue, is this really low areas, then green is middle, I think red is like these highest areas. Yeah, so just some things about Mercury. It has a density of about 5.4 grams per cubic centimeter, and it seems that like 60% of it is that nickel and iron core. It has very extreme temperatures, 700 Kelvin down to 100 Kelvin. It has a magnetic field, but it's a fairly weak magnetic field. It does seem to have water, or H2O, in solid form, so water ice, that is mixed with some organic compounds in these craters near the pole that don't tend to heat up quite as much as the other parts of the planet. It has a bunch of craters, kind of looks like the moon, but it also has some interesting features like these cracks. Right? So the crack down there on the right-hand side is through a crater, so it must have happened after the crater. The idea is that Mercury actually shrunk a bit and went through this process of like contracting after its formation, so the interior cooled down and the whole thing shrunk a bit. And so it goes through all this formation, it gets impacted by all these craters, and then it's cooling off and it shrinks. And so that's where you get these sort of like stress cracks, big cracks. So it does have an unusually high metal content, or what we think is unusually high. And the thought there is that it was impacted still early on in the formation, or a fairly large impact that pulled away a lot of the silicate, a lot of the rock. Right? So similar thing to like what happened to Earth, but whatever hit it didn't end up sticking around enough to form a moon. Last thing to note is, like I said, the surface of all these terrestrial planets has this similar feature where it's made up of this sort of like lower lying areas, sort of like oceanic crust, and then these higher areas are sort of like continental, thicker parts of the crust. All right, and then a bit about Venus. Venus is a hellish sort of planet. So this is density, about 5.2 grams per cubic centimeter. Size-wise, it's actually very similar in size to the Earth, and its composition seems to be pretty similar to Earth. You know, it has this core, mantle, the crust. It has a very thick atmosphere that is almost entirely composed of CO2, carbon dioxide. It's like 96% of CO2, and then a little bit of nitrogen gas and like even a tiny bit of some other stuff, right? But mostly carbon dioxide. And that ends up reflecting a lot of the sunlight that hits Venus. And that atmosphere is so thick, it's like if you were on the surface of Venus, then the pressure you're under is like 90 times the pressure that we experience here on Earth, which would sort of be like being about a kilometer under the ocean. Very high pressure, right? You'd be like squeeze. Wouldn't feel good. The image up on top here is an ultraviolet image, and the image down here is in the visible range. And so like if you were to look at Venus, then it's reflecting so much of the sunlight that it basically just looks like this solid thing. And that atmosphere is super thick and it covers the entire planet. So you don't see anything at the surface of Venus. Right? It was actually very difficult to get an idea of what the surface of Venus was until we finally started doing stuff like almost like radar surveys. We're bouncing radio waves off of it and kind of finally being able to image in a way the surface of Venus. There was a probe that I believe Russia sent early on that actually made it to the surface of Venus, but it only survived for, I don't know, like an hour or something like that before it was like melted and crushed. So it's also very hot. Well, I think we'll get to that in a minute. But that really thick atmosphere also is like crushing. Something odd about its rotation on its axis there is it's very slow. I think I mentioned this before, and it's actually in the opposite direction from the rest of the planets. So Earth is like rotating this way, and all the other planets are also rotating this way, and Venus actually rotates the opposite direction. And it rotates very slowly in that direction. So one day on Venus, like the time that it takes to revolve around completely, is almost a year on Earth, like 243 days on Earth. And then 1 year, meaning the time that it takes for Venus to go around the sun, is shorter than the time it takes to revolve on its axis. So like the calendar, if you were to live on Venus, would be very strange. Right? It takes longer for a day to happen than it does for a year. So like I said, we did eventually get an idea of what the surface looks like, somewhat from probes and also from doing sort of radar scans. And yeah, it's still pretty similar to Earth and to Mercury and to even the Moon, where there's these sort of highland, like continental areas and these lower sort of oceanic plains. It seems that there is some convection happening within the planet, like in the mantle, so similar to Earth, but it doesn't have this tectonic plate activity like the Earth does. Before we get into this, just pointing out in the image here, this is a radar map of Venus, and this is not the actual colors you would see, this is just color to indicate the heights. So the blue areas are much lower areas, they're like oceanic crust-like areas, and then you get higher and higher to like the red and the white, I think, even where you're at the highest areas, and these sort of large continental crust areas. I believe, I don't remember exactly, but I think there's sort of two main like continents on Venus, even though there's no oceans. There's a difference in the kind of the heights and the thicknesses of the oceanic sort of areas and the continental areas. And so there's a very large sort of continent that you can see, this red and white area and sort of green, and that I think that goes almost around the equator of Venus, and then there's like another one up towards the north side or the North Pole. So like I said, temperature is really high in Venus. It's like 730 degrees Kelvin or like 850 degrees Fahrenheit, right? That's even hotter than Mercury's high temperature. And Venus is further from the sun. We're sort of working out from the sun there. So why is it hotter than Mercury, right? You would think if you're further away from the sun, it's the sun that's generally heating up all the planets. And remember that inverse square law means there's less energy from the sun that's actually landing on Venus than there would be on Mercury, but Venus is hotter. Why is that? Well, at least the thought is that Venus experienced something in its past that we call a runaway greenhouse effect. You might have heard the term greenhouse effect or greenhouse gases before. Basically, there are certain gases that will make up parts of the atmosphere of planets, and we call them greenhouse gases because they tend to reflect a lot of infrared radiation, like a lot of heat. One of the main ones is CO2, carbon dioxide, which is the majority of Venus's atmosphere. There's also ones like methane, and even water vapor is actually a greenhouse gas. So on Earth, currently at least, a lot of that CO2 that we have on this planet is frozen, sort of locked in polar ice caps, or is dissolved in our oceans. And so there's a normal greenhouse effect that happens all the time, which is part of what keeps planets sort of warmer than they would be without their atmosphere. The normal greenhouse effect is when there's just some of this stuff in the atmosphere, something like CO2 in the atmosphere, and the sun, or radiation from the sun comes in, sort of like visible light and ultraviolet light, and it will go through the atmosphere and hit the surface and heat up the surface, or depositing energy, warming up the surface. And what happens then is the surface cools down, and it cools down then by re-radiating that energy. But it doesn't push it back out as the same wavelengths. It goes to longer wavelengths, which are infrared. So it's re-radiating this energy back out, but it's radiating the infrared part of the spectrum. And so in a normal sort of atmosphere, there's some of these greenhouse gases in the atmosphere, and that infrared radiation, remember, is reflected a lot by those greenhouse gases. And so that infrared radiation will kind of go up, and some of it will get reflected and end up kind of sticking around in the planet, or within the atmosphere. Right? So the planet overall stays a good bit warmer than it would be without that stuff in the atmosphere. That's a sort of normal setup. You can get into trouble, though, or you think that you get into a lot of trouble, though, if you increase the amount of these greenhouse gases, and you kind of keep steadily increasing, or maybe exponentially increasing the amount of these gases in a planet's atmosphere. And it's a sort of snowball thing that happens, right? That's why it's called the runaway. It's like once this process like kind of gets going, then it just kind of snowballs and becomes not a good place to be. And that basically happens because if we think about, say, adding more CO2 to the Earth's atmosphere, then more of that infrared radiation is getting trapped within our atmosphere and sort of sticking around, and so the Earth overall stays warmer. So, and if that process continues, the temperature will warm up enough where we'll start to melt our ice caps, or polar ice caps. Remember, there's a lot of CO2 in the Earth that's locked in those ice caps, right, and frozen in there. And so if they start to melt, then you release even more CO2. And so you kind of keep pushing this process along, where it sort of then becomes like this self-perpetuating thing where you're melting the ice caps, and so you're releasing more CO2, so it's getting even hotter. And eventually you get to the point where there's so much CO2 in the atmosphere that the planet gets so warm that you can even then start to evaporate, like boil, the oceans, and then you're also releasing all the CO2 that's in the oceans too, and then you're just getting hotter and hotter and hotter, and you basically are boiling all the oceans away, all the liquids away on the planet. And what you end up with is this atmosphere that's very high content of CO2 and a planet that is incredibly hot and inhospitable, Venus. And then just a little illustration here I forgot to mention about infrared radiation. You might have seen images that are infrared images. This is one of a cup with some hot liquid in it, and so that infrared radiation is basically heat, sort of heat that comes off of like a glowing iron, or like the heat that radiates away from this cup with liquid in it. And you can see the areas, the hotter areas, are the more intense infrared radiating areas. They're indicated with the color here, so from that dark and purple is lighter temperature up to that yellow and even white, higher temperatures. So the cup where all that liquid is right in contact with the hot liquid, so the cup's very hot and radiates the liquid. You can see a little bit inside is the hottest part. The handle, much cooler, much lower temperature, less infrared radiation coming off of it. Yeah, so that's kind of stuff that gets reflected back down to the surface by the greenhouse gases. Lastly, we're going to talk a little bit about Mars. So Mars is the last of the terrestrial planets that we haven't talked about. Right? That goes Mercury, then Venus, and Earth, which we started talking about. So jumping over Earth to Mars. It's a nice picture of Mars. This one is more of like that radio sort of image almost. I don't know that it's radio. This is just a visual illustration with the color to indicate the altitude, the height of the places on Mars. And like the other planets, and like I've said, it has this sort of similar structure as the other ones do, where there's these higher, like large higher places, like continental or continents almost, and then these lower regions, these lower sort of plains, like they're more like oceanic regions. Mars actually is fairly low in density and is made up of much more silicate rock, relatively speaking, than say like the Earth. There's a relatively small metal core. It's only about half Earth's diameter, I think about 1/10 of the volume. The red sort of color you can even see with your naked eye when you look at Mars comes from a decent amount of iron oxide on the surface. Mars, as you can see in the image on the left there, has polar ice caps that are made up of not just water ice, but also carbon dioxide. Frozen carbon dioxide, by the way, is what we call dry ice. The day on Mars, meaning how long it takes to rotate around on its axis, is very close to Earth's, about 24 hours. There isn't a magnetic field currently, but from evidence we found in magnetized materials on the surface, it seems like it did have a magnetic field at some point in the past. Relative to Earth, it has very extreme geography, and you can get an idea of that just from like the highest mountain on Mars is this Olympus Mons, which is like 3 times the size of Mount Everest, or at least as high. Like wide, I think the book mentions it would cover like the whole state of Missouri. And I think it's like one of those, I don't know, one of those like white circles, I think is probably Olympus Mons. Another extreme example is this trench, this canyon, Vias Marineris. Bad accent, sorry. You can also see that in the altitude picture here. There's this like scar almost, it looks like. And that is a canyon that would stretch from about LA to Washington, D.C. Very large scale geographical features. So something that's very interesting about Mars is that it seems like there's been a decent amount of evidence and research and things that have indicated that it might have actually been a lot more hospitable in the past, at some point in the past. So Mars doesn't have an atmosphere now, which means that it ends up being very cold. There's nothing to keep any of the heat in. So it ranges from minus 28 Fahrenheit to minus 148 Fahrenheit. So it's still like well below freezing. Point about the dust storm seems a little bit out of place to me now, but just to mention that Mars is covered in this layer of dust, and there's dust storms that occur regularly on Mars, and they can be huge. They can actually be large enough to have storms that cover the entire planet. And so that's how you get this layer of dust pretty much on everything on Mars, which makes it difficult to survey. But getting back to hospitable nature, it's thought, at least, that Mars at some point in the past had a pretty substantial atmosphere. And that means it would have kept a lot more heat, it would have been a lot warmer, and possibly warm enough for liquid water to exist, which is what we think is a key component to life forming, how we're existing here at least. Some evidence that there was at least liquid water at some point. There appear to be some channels, like waterways. The image up on the top right there is of one that is fairly large. I think it's like maybe a mile-ish or so across, and it seems to look a lot like a dried up sort of riverbed, river or a channel of water. B here is showing what appears to be sedimentary rock. I don't know if I mentioned too much about that, but sedimentary rock is rock that's formed by sort of dust and stuff getting deposited in layers, and you gotta keep getting all this stuff deposited, and then eventually there's enough pressure of stuff above it that crushes it down and squeezes it together. And it's sort of like making rock by just like squeezing rock together. Right? It's not volcanic rock, it's when it get melted and then fused together. It actually just kind of got squeezed together. And that tends to happen, I believe, I'm not a geologist, this is not necessarily my expertise, but it seems very likely that that happened with the help of water, right? Water depositing sort of layers of dirt over and over and over again, and that dirt eventually sort of gets squeezed down. So you can see those sort of like slats, kind of looks like in the image there, and so that gives us a pretty strong indication that there was actually water around this area at some point. Then the last example here, there are other reasons to think that there's probably liquid water on Mars at some point. These are just some of the main ones I picked out. This last one is a meteorite that landed on Earth. Remember, a meteorite's just like a chunk of stuff that made it into the atmosphere, and then a meteorite is when it lands on the Earth's surface. This is a meteorite, and sort of by process of elimination, we're pretty sure that it came from Mars. So probably there was some sort of impact on Mars, threw out some of this debris, and some of that debris eventually landed on Earth. And in that meteorite, there is H2O and some organic compounds. As I mentioned, Mars is substantially smaller than Earth, and what's thought to have happened is that, it did initially have this atmosphere, and in that time, early on in the solar system, maybe it then also had impacted with comets that deposited H2O and was able to build up like lakes and oceans. But being much smaller means it has a much lower gravitational pull on things, and so it's kind of over time that atmosphere just sort of leaks away until eventually you don't have any atmosphere at all, and then you can't keep liquid water anymore because it gets so cold. Right? The atmosphere helps keep a lot of that warmth in. The last things to point out, just some interesting features. So one of the pictures up on the upper left there is of one of the rovers that we've sent to Mars. And so I think on the bottom left is like the landing craft that brought this sort of rover down. And then you can see like the ramp where that little guy kind of got out, and see the rover itself over in the image, Pathfinder. Yeah, it's thought that area is actually possibly like a past lake bed or something like that. But something else that was very interesting when it was discovered was what they call these gullies, which are shown in both the other images, where these sort of like dark streaks on the slopes of like canyons or craters, which at least initially like really seemed like they would have been formed by some kind of liquid rolling down, kind of flowing down. So there was some thought, and some people still think that those are actually formed maybe by some liquid water. More recently, it's been put forward, and it may be sort of the leading theory now for what they are, is that they're actually due to carbon dioxide. And particularly, you have carbon dioxide, like in solid form, it's dry, like dry ice, and it's like near the surface, it's like just kind of under the surface, there's a decent amount of this dry ice. And at points, those areas can get warm enough, like the sun maybe will warm them up enough that that dry ice wants to change phase, it wants to get out of that solid form. But if you've ever seen dry ice, then you might notice that it's very hard for it to be a liquid. right? Like if we have dry ice here, if I had some to show you, it'd be a chunk of things, and then there'd be this like vapor, this gas leaving from it. And that's because dry ice, most of the time, doesn't go through a liquid phase. It goes from a solid directly to being gas. That's what we call sublimating. So the idea here is that there's that dry ice that's in the soil, underneath the soil, and then when it gets warmed up enough, it sublimates, it becomes a gas, and that gas sort of temporarily mixes with some of the dirt and almost then acts sort of like a liquid, and then it's able to kind of like run down the slopes a little bit and start to form these gullies that we see. That's the thought now, at least. But that's not to say that we're still pretty sure that there, or we know that there is water ice in places like the poles and such, and it does definitely seem like there was liquid water at some point. It's just too cold now for that water to not be a solid anymore. One very active and interesting area of astronomy is looking for life outside of the Earth. And given the fact that we're pretty sure Mars had liquid water at some point, like lakes and oceans, it's a pretty good chance that it had some kind of life at some point. Like maybe just microbes, single-celled organisms, something like that. So it seems pretty likely that it did. We haven't found any concrete evidence of that yet, and fortunately or unfortunately, the best chance of actually getting some conclusive evidence is still going to be bringing stuff back to Earth so we can actually study it in great detail. We've tried sending rovers there that have instruments to be able to try to detect if there's life, and there's ways of going about trying to see if there's things like respirating, other things that are taking in energy and like transforming it. None of those have really been successful, which is why currently at least it still seems like the best chance is going to have to bring some Martian rocks back and really study them. I think there's ideas to do that now, and most likely from the places where we think that there was a substantial amount of liquid water at points. And that's all I got for this lecture, so see you next time, I think, when we talk about some big old gassy planets. Thanks.